Welcome to Public Health on Call, a podcast from the Johns Hopkins Bloomberg School of Public Health, where we bring evidence, experience, and perspective to make sense of today's leading health challenges. If you have questions or ideas for us, please send an email to publichealthquestion@jhu.edu. That's publichealthquestion@jhu.edu for future podcast episodes.
This is Lindsay Smith-Rogers. What do a mosquito's sense of smell and the transmission of malaria have in common? Today, Stephanie Desmon talks to Dr. Conor McMeniman of the Johns Hopkins Malaria Research Institute about his fascinating research into why some of us are more attracted to mosquitoes and how a greater understanding of the mosquito olfactory system may save lives. Let's listen. Conor McMeniman, thanks so much for joining me.
Thanks for having me, Stephanie.
Today, I want to talk to you about mosquitoes. We know that some of us are tastier than others to mosquitoes, and there's been all kinds of speculation about what causes that. And I'm wondering if you could sort of start by telling us, what have some of the theories been and what have you now found?
Yeah, absolutely. So for possibly millennia, humans have been asking the question of, why some humans might be more attracted to mosquitoes than others. A number of different anecdotes sort of get flown around during our daily conversations and backyard barbecues and also hikes. These include theories such as my blood is sweeter than another's blood, for instance. I might have better tasting skin than another person. Also, maybe how attractive I am to mosquitoes might have something to do with my blood type, or perhaps the way that I smell to mosquitoes. All of these anecdotes and theories, have been sort of, discussed for a long, long time. And as scientists, we're really interested in developing new ways to actually test associations, biological reasons. Some people might be more attracted to mosquitoes than others. And that's the major focus of my laboratory's research and the recent study that we performed.
So why does it matter?
So it matters because, if you're bitten by mosquitoes, you're at, firstly, enhanced risk of nuisance biting, and we all hate being bitten by mosquitoes. But from a global health perspective, it matters because mosquito-borne diseases are attributable to around 1 million deaths worldwide per year. Of these mosquito-borne diseases, the most significant and also the most deadly is actually human malaria, caused predominantly by a parasite that's transmitted around the world, that is causes most death and sickness in sub-Saharan Africa. And of these approximate 600,000 deaths per year, most of these are experienced by children and also pregnant women. The mosquitoes that transmit malaria, and in particular, the apex predator of the mosquito world, the African malaria mosquito Anopheles gambiae, loves to frequently and preferentially feed on humans. And to find humans at a distance, this mosquito species uses its really exquisitely tuned sense of smell.
Interesting. So if you can figure out what's behind that, maybe you can come up with ways to protect everyone better from mosquitoes.
Yes, absolutely. So as mosquitoes use their sense of smell to locate us from a distance and sort of track towards us, hunt us in the environment, understanding the mechanics of how their smell system works could be used to develop new effective ways to block that sense of smell and also potentially manipulate them to being trapped to control these diseases. Also, by understanding the molecular mechanics of how the mosquito smell system works, what the molecules are that they're detecting in human body odor, and also what the molecular receptors are in the mosquito nose or their olfactory system, perhaps we can develop new molecules to scramble mosquito smell or olfactory coding, and also potentially mask the human scent signature to make us somewhat invisible to mosquitoes.
Wow. So in your recent study, what did you do?
So in our recent study, we developed a system in Zambia, in a region called Choma district, which is about 2 hours from Victoria Falls in southern Zambia. We developed this very, very large greenhouse-like facility. It's a screened greenhouse about the size of 2 tennis courts in area, if you think about the area of this structure. And we like to think of this structure as the world's largest multi-choice smell test for mosquitoes. Flanking this very big, large screen greenhouse are one-person tents where individual humans can sleep. We connect these one-person tents to this central screen greenhouse by repurposed air conditioning ducting. And that repurposed air conditioning ducting is actually used via a low-speed fan, which is installed in those tents to suck the whole body scent emissions of individual sleeping humans out of these tents and into the central greenhouse. And the scent of each human is actually ducted and vented and wafted over the top of a small heated target that mimics human skin. It's made of aluminum, but it's warm to human skin temperature, 35 degrees Celsius. And we have cameras positioned over these structures that record landing of mosquitoes on these structures, which is a good sign that they're ready to bite and are lured by the scent of those humans. By competing up to 6 of these different tents and associated landing pads against each other, each baited with human scent, we can then ask the question simply by monitoring mosquito landing on these platforms, which human scent do the mosquitoes prefer?
That's crazy. That's crazy. So what did you find?
Yeah, so we found that night after night in these particular assays and this initial validation of this system, that certain humans were frequently targeted by the mosquitoes and their scent appeared to be very, very attractive to the mosquitoes. Conversely, on the opposite end of the attractiveness spectrum, we found an individual human that wasn't very attractive to mosquitoes as well. While we're actually performing these behavioral assays, quantifying mosquito landing in response to individual person's scent, we're also capturing that scent and collecting it for chemical profiling in the laboratory here at Johns Hopkins, such that we can actually derive individual chemical scent signatures of those individuals by using analytical chemistry techniques. And then we can actually identify which odorants are associated with being highly attractive to mosquitoes or alternatively not very attractive to mosquitoes.
And so what can you tell us from this? I know it's probably early, but what can you tell us?
Yeah. So in this initial validation of this system with the 6 humans, we found that the most attractive individual, a so-called mosquito magnet, actually had a scent signature that was predominated by a class of airborne chemicals known as carboxylic acids. And in particular, a handful of very light carboxylic acids that are very airborne and are released off the skin at increased rates. These carboxylic acids are putatively produced by the natural bacteria that live on our skin, the so-called skin microbiome, and also produced in sebum. Sebum is an oily secretion that is released by the sebaceous glands on our skin, and it actually hydrates the skin and also protects it against microorganisms. We also found another compound or chemical called acetoin. Acetoin belongs to a class of chemicals called the ketones, many types of ketones in human odor, but acetoin as well is putatively produced by skin bacteria too, which is quite interesting. So we have these 2 classes of molecules, carboxylic acids and also these ketones that seem to be at increased abundance in the scent signature of the most attractive human, and these are possibly produced by the skin bacteria that live on our skin. On the opposite end of the attractiveness spectrum, we found one individual with a radically different scent signature. And this individual actually was depleted of these carboxylic acids that we found in the scent of the most attractive human, and also was depleted of a number of other chemical classes found in human odor. So overall, a very low, perhaps not very smelly person to the mosquitoes. But very interestingly, they had a compound or chemical in their body odor profile called eucalyptol. And in particular, they had a lot of eucalyptol. Eucalyptol is a compound that is found in a wide variety of plants, including herbs and different spices, such as sage and cardamom and sweet basil. And we hypothesized that this particular individual may have obtained eucalyptol as part of their plant-based components of their diet. Also, eucalyptol is also included as a flavoring in a number of different foodstuffs that we eat around the world. It's also in toothpaste and mouthwash. So it's an interesting anecdote. And I think that in the future, what's really required to make more definitive associations is, an increased sample size, and perhaps also performing more controlled trials where we track dietary information and ultimately to make causal associations between diet, for instance, and attractiveness to mosquitoes, we'd have to perform a clinical trial. But overall, I think this study really hints at the exciting potential mechanisms that bacteria might contribute to our attractiveness to mosquitoes, and also potentially diet may play a role.
That's fascinating. So, we could all be eating sage perhaps someday to keep mosquitoes.
That's right. I think it's something that we're particularly excited to test moving forward, is expanding the number of humans that we test in this multi-choice system. This system actually increases the comparative power of screening for humans that are attractive to mosquitoes by about 15-fold relative to two-choice assays, which there's only one comparison occurring. So we're very excited to eat a lot of sage in the future and actually test what happens.
Absolutely. So what is sort of the role of human scent in sort of this, coupled with this problem of the malaria burden? So, how do the two go together?
Yeah, absolutely. So at a distance, mosquitoes actually detect humans using their sense of smell. And within the context of malaria, the majority of malaria in Africa is transmitted by a handful of mosquito species, all belonging to the Anopheles genus. Anopheles gambiae, the African malaria mosquito, is the major mosquito that transmits malaria throughout much of sub-Saharan Africa. Anopheles gambiae hunts humans during the nighttime, typically when humans are sleeping. During this period, humans are often housed indoors together in groups. And scent actually emanates from the human body in our skin odor and breath. And from these humans, it dissipates into the air, rising on warm convective currents. And these scent plumes containing human odor then dissipate through gaps in the walls of housings, and also the gaps created between the roof and the walls, the eaves of the house. Being carried then downwind of these housing structures, these scent plumes are picked up on by the mosquitoes, and they're really alluring. They draw Anopheles gambiae into the proximity of a human host. Carbon dioxide, which is part of human breath, probably dissipates around 60 meters from a human host within that range. And that's probably based on its very light nature. It's a gas, the first thing that mosquitoes pick up on. And as they detect carbon dioxide, they get activated and they start moving, weaving along these scent trails till they eventually start to encounter other body odorants that perhaps are less airborne but still emitted at a great rate, until they eventually encounter more chemicals that are less airborne as they get closer to the human host. About 5 to 10 meters from the host, they can see the host. And then when they get within 1 meter, they can sense the warmth from our skin. So first they smell us, then they see us, and then they feel the warmth from their skin. The mosquito nervous system is actually equipped with very specialized sensors that detect chemical cues, visual cues, and also thermal cues. All of these different chemical and thermal cues actually get detected and integrated by the mosquito nervous system to actually lead to landing and then taking a tasty bite from their preferred victim. So in the sense of this particular study, variation in that attractiveness of a human is really an important factor that could drive epidemiological risk for infection, the risk of exposure to mosquito bites. And as such, it's also a very important component of how fiercely malaria transmission is potentially maintained. Malaria is innately driven, transmission of malaria is innately driven by the infectious bites of female Anopheles mosquitoes that need to blood feed to produce eggs. Therefore, an improved understanding of the mosquito's sense of smell and the role of chemical differences in underlying how frequently you are bitten by mosquitoes is really important to breaking the transmission cycle.
What's next for you guys?
Yes, so in the next few years, we're really excited to expand this particular study. We have plans in the next 2 years to increase the study size to actually evaluate the attractiveness of 120 humans over 2 Zambian wet seasons in this system. During this study, we're going to more deeply explore chemical space associated with attractiveness by using a variety of very advanced ways to profile what types of molecules are present in human body odor and get a really comprehensive understanding of the human scent signature. We're also really excited to further investigate the link between the bacteria that live on our skin and our scent signatures. And as such, we're going to profile whole body microbiome signatures as well by swabbing individual volunteers in this particular study at 12 different body sites, sampling their oral, the microbiome in their mouth, their nasal microbiome, the microbiome in their nose, and also their skin microbiome on things such as your arms, your legs, your feet, and various other body parts. Hopefully, we hope this will really improve our understanding of both the chemical and also the microbial signatures that make us so attractive to mosquitoes. We're also, from a translational perspective, trying to use this information to create super attractive blends of molecules or fragrances that mimic the scent signatures of highly attractive humans. And we hope that those will be really useful as a way to bait mosquito traps to improve our ability to combat malaria, both from a surveillance perspective, where you need to trap mosquitoes to see what type of mosquitoes are out there, and also potentially from a mass trapping perspective to actually put a dint in the population size to turn the mosquitoes' sense of smell against them and lure them to their death.
Well, that is quite a perfume you're about to create.
That's right.
Conor McMeniman, thank you so much for joining me.
Thank you, Stephanie.
Public Health on Call is a podcast from the Johns Hopkins Bloomberg School of Public Health, produced by Joshua Sharfstein, Lindsay Smith-Rogers, and Stephanie Desmon. Audio production by J.B. Arbogast, Holly Cardinale, Philip Porter, Spencer Greer, and Matthew Martin, with support from Chip Hickey. Distribution by Nick Moran. Production support from Catherine Ricardo. Social media run by Grace Fernandez and Shian Briscoe. If you have questions or ideas for us, please send an email to publichealthquestion@jhu.edu. That's publichealthquestion@jhu.edu for future podcast episodes. Thank you for listening.